almost not able to finish my food. I am used to eat a lot. Good morning. Thank you for coming, even after yesterday's brewery. Hopefully you enjoyed it at least a little bit. I hope it was enough food. And yes, so today program is quite clear. We have 3 lectures, so it's the most rich program today. After Gianni's talk, there will be Alejandro and Jen presenting. Again, we have this split to 2 groups. I think Alejandro that he will provide his talk twice. So, like the talk at 10:45 will be again split to 2 parts. So part of you will stay here, part of you will go to seminar rooms. It should be the same seminar room as last time, so it will be exactly the same procedure. Yes, and at the evening we are going to see Prague, so hopefully you are not too much tired from yesterday and you are ready for another round. I am not sure if I am. So můžeš, taky ho tam dáš? Okay, so we will, možná to řekneme potom, protože tady bude, Jan has prepared some information for the evening, but as I see that not all of your colleagues already are here, so we will tell it like around lunch, I would expect. So don't ask me before for the evening, it will be specified later. Thank you. So thank you very much for coming, Gianni, and I'm looking forward to see your presentation.
Thank you, Martin. So good morning, everybody. As you can see from the slide here, maybe if I slide, okay. This talk will be about human-swarm interaction cooperation. I assume that in past days you had enough about swarms and all the related things, okay? So I'm not gonna really go into what a swarm is, what we can do, and so on, but in order to be on the same page for what I'm gonna talk during the presentation, let me start with little things, my own view of what a robotic swarm is. Okay, this will be useful to understand each other during the rest of the talk. I still remember, was like in IROS a few years ago, we had this workshop about multi-robot systems, and then at the end of the day, we all agreed that one robot is, of course, one single robot system. 2 robots is a multi-robot system, and 3 robots is already a swarm. So this is to say that actually it's kind of like difficult to make a clear separation between what is a swarm versus a multi-robot system. For me, I'm a very pragmatic person at the end of the day. For me, it's like a swarm is potentially a very large system of cyber-physical devices. When I say cyber-physicals means I'm emphasizing that have like some communications, different layers of softwares, some different mechatronics. Each device may be not extremely sophisticated, but this might be just for budget reasons, not for design or theoretical reasons, because by the way, if you think that all these self-driving cars that we will have soon, most likely in the roads, they will create a swarm, and each one of these cars is indeed very complicated entity. So it's potentially a very large system. And what are the design objectives that we put on this very large system? Well, what we want is a scalability of performance, precisely because it's very large. We don't know to which extent this can become a large system. And we want to take advantage of the architecture which is inherently parallel and distributed. So by design, I need to exploit this. And also, I need to exploit the fact that since I have a potentially very large system, I have a redundancy of resources that is good for tolerance or for showing robust behaviors. Okay, so at the end of the day, it's very simple. Large system and some design objectives. Now, what should be the design approach to meet those objectives? The design approach is the typical design approach which is being followed in the field of swarm intelligence, is at the end a bottom-up approach. So what I want to design is relatively simple, uninformed of the overall goal individuals, and relatively complicated, maybe, interaction protocols. And I do this in a bottom-up way. And mostly, I will have a locality of interactions. When I say mostly, it's because, again, no religion here. If it is convenient, it is possible, we have some centralized parts. Why not? If the system, working well. And by design, I need to leverage emergence and/or self-organization. Okay, so these are somehow, if I follow these things, for me, I'm doing some swarm robotics. That's all. And what I want to do is, if I want to point out this aspect of self-organization, I think this comic illustrates the situation very well. And I have this, I love this. I've been like playing this since. How can I remove the audio? Because otherwise... No.
It's smarter to travel in groups. Take the bus. The lane.
All right. Well, we might have a problem with all these sounds in the following, but fine. I hope not, but some of them. Okay. So, everything, this is nice, but somehow, given that we have this design approach, we still have to come up with some good interaction rules and individual behaviors that once they are composed non-linearly, what I get is the desired system level behaviors with all the properties of scalability, robustness, redundancy that I said before. So very simply, of course, if I follow these rules for designing a swarm, I have some downsides. The downside is, of course, in terms of maybe predictability, formal guarantees, where the system will go, precisely because I'm adopting a bottom-up approach for designing the system. And also, the finite time performance might be an issue. So what will happen in 1 hour? You can say, I don't care. No, I do care, because if you tell me that in infinite time the system will converge, I'm happy, but I also need to know what will happen the next hour. And this is inherently difficult because at the end of the day, a swarm is a complex system. Therefore, a complex system can have some, this is from like strange attractors, so the dynamics can be very complicated, so predictability is actually a problem. And also, efficiency in problem solving might not be super. If we look at, okay, I hope it's not going to explode with sound. Okay, but this is fine. But okay, this is like the famous, I mean, the video showing like ants. You already know that ants are a major source of inspiration for robotics.
This one kan man pulje ret i.
Ja, det gør det virkelig klart.
Det gør det ikke.
Man får lidt stress på deres vegne.
No, it's not here. Here is already like this. Okay, I can do it here, yeah. But there's no way to do it here? No, all right. So these guys can make a bridge connecting a gap. This is a fantastic behavior. This is like one of the most brilliant examples of self-organization, of emergent behaviors, but it takes ages. It's definitely not efficient. If I have to do this, from an engineering point of view, if I have my budget put in there, maybe this is not the way I would go, okay? So this is to say that there are some downsides of swarm design, in spite of the fact that we can get a number of properties in terms of scalability, redundancy, and robustness. So if we want to take the swarms from the laboratories to the real world, maybe we need to work out some aspects. For instance, here I'm showing some potential applications of robot swarms. All these applications have in common the fact that basically I have to deal with some spatially distributed region where I could deploy my robots, and each robot could do more or less independently their job there. Okay, it makes sense. It's like, you know, farming in different ways, cleaning, patrolling a vast area, or anything about logistics, warehouse operations, search and rescue, post-disaster management. Fine. But in all these cases, reliability, efficiency, and predictability are highly desired. You don't want to deploy your swarm and say, hey, how long is it going to take to clean up this? Maybe 1 day, maybe 1 week. Well, no, I don't want this answer, okay? So how do we tackle this inherent problem in swarms when we take, as I said, this bottom-up approach in design? Well, one solution, but also brings a set of problems, is to include the human in the loop of operations of the swarm. If I add a human somewhere in my chain of interaction with the robot, then I can basically exploit a number of aspects. First, my human is expected to have a clearer view of the high-level goals of the mission, of the system, which is indeed in contradiction, is different from what I said at the beginning, where the individuals in a swarm are uninformed. The human is fully informed. So I can exploit this fact. Also, the human has some probably superior cognitive abilities and some specific sensory motor skills that can be used during the interaction with the swarm. So we can use a human to guide, instruct, correct, bias, influence, participate together with the swarm in order to enhance its capabilities and to overcome some inherent flaws, I would say, that are in the swarm design in order to pave the road to the application to the real world. But here I put this and a set of problems. Of course, every opportunity comes with issues. How do we include this agent with all these capabilities in my loop of operations of this possibly simple, uninformed, and very large number of agents? So I should define what will be the human roles, what this human will do. And also, hey, what are the autonomy levels of the swarm, because I should reason on what I can do according to what the swarm can do, and vice versa, what I can do in the task. So I need to reason on these two aspects, which once I take them together will define what kind of controls the human can operate with respect to the swarm. And then this comes, if I reason in high level on these aspects, then it will come like, hey, what kind of interactions should I set up in order to obtain this, in order to let the humans performing its roles at the best? And when I say interaction means, hey, I should define what are the interfaces that I use for a human to communicate to a swarm, and vice versa, a swarm to send information to a human. So you see, the problem starts to be a bit complicated because it involves many different aspects that need to be taken into account. But it's an opportunity, and we have to use it, because otherwise, hardly we will see swarms appearing in the real world. So all these aspects have been studied in human-swarm interaction, which is a relatively recent field. I took this custom to go on Google Scholar and check how publications refer to certain keywords per year to see how the relative impact in science. So this is actually the number of publications per year, is not cumulative, per year on human-robot interaction. You see that, okay, they started from 5,000 and they are keeping increasing also because, I mean, robotics is boosting, and then this is a field that's way more and more interesting. Then if you look at what happens in swarm robotics, we start in year 2000 with almost 0, very little, and then actually is growing up to 8,000, so basically this part. Then if we look at human-swarm interaction, so a subset inside of the domain of swarm robotics, we see that actually the numbers are 2 orders of magnitude less. So this is to say that, and by the way, I had to start here from 2006. Before there was basically nothing. Okay, so Google Scholar is not definitely the most precise way to measure these kind of things, but this tells how young this field is, and also tells us that there is a lot of things we can definitely do. But also tells that human-swarm interaction is not a well-established discipline. So, as a result, the rest of this talk might look a bit also confusing, precisely because I had to somehow find out a way to tell you a story, to point out challenges, to point out issues, in order to say, hey, once you get out of this room, at least you know what are the problems, what is on the table, and you have some ideas of what people has been doing so far. In principle, if you start being engaged in this field, you can almost read all the papers that are there, so you have like a very nice view of what's going on. So let me start first with actually trying to single out what would be desirable features for a human-swarm interaction system. There is this paper from 2008 from Shishir and Venagayamurthy. I met these guys, I was there, where they actually listed, so 12 years ago, a set of features that are still valid today, okay? But let's do a little bit of interaction also here. Based on what I said, based on what you have heard during the past days, so what features you would single out to be in a swarm interaction system? So who can tell me, yeah, I would like to have this. Think you start designing, you start engaging with this, what do you think should be there? Don't be shy. What? Who said? Who? Yeah? Fast response. Fast response. All right. Okay. That's something. That's a very good point. That's a very good point. I ask a swarm to do something, and actually it does what I'm asking, which is not a trivial point. Because if now I tell you something, you have different heads, different ways, different perception. And imagine I can, by the way, tell you this with gestures. For instance, what are you going to understand about my intentions? So will my intention will be transferred to you clearly, and will you be able to actuate, execute my intentions properly? Very good. Yeah? Good. The point is, we want to have like a system level behavior, and at the same time, so we will need to do something at the microscopic level, but not too microscopic, because there are too many elements. Other ideas? Yeah? So I tell something to one individual, and then the information propagates. Okay, this is also a very essential point in swarms. If I inject information at some point, then the system must have a structure to propagate this information in a coherent way. This is also very, very good. Yeah? Yeah? Okay, so she's pointing out, hey, if the swarm is doing something, should have some explanatory aspects in order to make the user aware of what's going on and why. Because we'll see, actually, this is a very good point. We might learn about this, observing that maybe things didn't go the way I was expecting, and then next time, me, as an operator, I should change it. Okay, I think we are on a very good path to understand this. So let me list these things that I took as they were in the paper. So somehow it's not even my ideas. But so the idea is like human-swarm interaction should promote positive emergence of intelligence. As I said, it's a self-organizing system. So somehow the way we use it, we interact, should leverage this. Okay? Which goes also in the way we should focus on the macroscopic output rather than on individual things. Should facilitate local rather than global interaction, because at the end of the day, if the first is true, then global things will happen. Should be scalable, of course. This is why one of my design goals, I don't know how large it can be, so definitely should scale. So scalability is one primary aspect to take care of. And should be able to work well even without human input. Yes and not, but in general, we want the swarm to have some levels of autonomy doing things. The human input should be perceived as something that helps, provides a speed up of performance, improve performance. Otherwise, we have two systems that are too much banded together. Should support multiple users to interact simultaneously. Makes sense. Why not? Why should I have one single human operator doing the job? Should be able to present useful information to the users for situational awareness that your colleague was pointing out. So the information that I'm receiving from the swarm should be able to build up a view of what's going on. Which is not obvious, because if I have to summarize your status, let's see how we can do it. And also should allow users to adopt some divide and conquer strategy. Somehow the idea would be to split the job to focus on small groups, and then these small groups will propagate to the entire swarm. And interaction should provide some easy interface to provide some tactical input and domain knowledge to the swarm. So the way I can transfer information should be easy, because otherwise if it's too difficult, I cannot really transfer complex or relatively complex things. And the architecture should be generic. So if I devise a way to interact with the swarm, this should be usable in many different domains, should not be super tailored to one specific subdomain. So I think these are all reasonable things, right? So if we somehow think a bit more, we can put them together and have, yes? Sure. makes totally sense. I mean, it should be there since we are talking about robots, so physical agents that can hurt me, definitely. But somehow this is, let's say, should be part of the levels of autonomy of the swarm, the capability of the swarm to do things, and also my situational awareness. How much do I understand what's going on? Because if, let's say, I don't understand things, and I put myself in the middle of the swarm things, and then I say, it's your fault. No, it would say it's also your fault that you didn't do things properly. But if we pack up things, I try to somehow to summarize in this diagram the entire topics, issues, problems, components of a human-swarm interaction system. So what we have here is, we have some mission goals and constraints. Remember, I want this system to be deployed in the real world, do real things, okay? So I have mission. This is always, I use this word, mission, okay? It's not just purely academic. So I have goals and constraints. So these goals and constraints, of course, will interest all the aspects of my system. For one side, I have human agents, and from the other side, I have the robot swarm. The human agent, as a designer, I have to decide what kind of roles the human agent will take. Now we will see what I mean about roles a bit more in detail. And different roles will imply different cognitive effort from the side of the human agent. Of course, imagine if I had to control each one of you one by one. This would be like an immense cognitive effort from my side, right? If instead of I take a leader and say, you follow this person, the workload would be minimal, okay? So according to what my role, this has an impact on cognitive effort. So we have to clarify what are the roles, how we can measure somehow the cognitive effort. Because at the end of the day, when I want to design this guy, I need to take the proper role for the task and such that it's affordable for a human being. For the robot swarm, I need to understand, define what are the levels of autonomy. So what the swarm can do by itself. Because this is essential. If I know what the swarm can do by itself, this came out also before, then I can decide in which sense, to which extent I can interact and be in the loop of operation of the swarm. Of course, okay, I should also take into account what are the intra-swarm interactions, how information is propagating, as we were saying before, inside the swarm. So between these two agents, I would say, we have the interaction interface. So what is the interaction interface? When I decide what should I do, what are my roles, how I execute my roles, what kind of information I do transfer to the swarm. So which are somehow my controls, the goals. And this will happen, by the way, through a physical interface. Now I'm talking to you, right? I'm using speech, visual, gestures, some supports, right? So we have to decide what to use in order to perform actions that are consistent with my roles and with the cognitive effort. And this goes from the human agent towards the robot swarm. On the other side, from the robot swarm, what I have to transfer back is state information, feedbacks. Did you understand? Yes. It's not a state information, it's like acknowledgement. So feedback. State is to which extent everybody is sleeping, 70%. Fine, this is state information. So I need to transfer this kind of information and also perceptual data. Any kind of data that the swarm can gather, I can need to transfer. So all this somehow I can put in a big block saying is for situational awareness for the human. So if we take all this together, basically we have to decide a number of things. What the humans will do, an appropriate cognitive effort, how the information will be transferred, what would be physically the interaction interface, what kind of information is going in the other way. And this all in the light of the mission goals and constraints. So you see, it's kind of complicated problem, right? It's when I say human-swarm interaction, okay, yeah. No. We have a lot of decisions to make here. And each one is very much complicated. When I say situational awareness means hey, now you transfer me information that's, with this information, I know precisely everything I need to know, so I have a complete information about the swarm such that I can take my next action consistently. And also I need to represent this information. I need to transfer it, I need to represent to myself. Every component is quite complex. All right. So let's try to now to somehow to explode individual blocks and try to get a little bit more information about what the roles could be, what is the terminology, what is the taxonomy, the relations with human-robot interaction, and other things. So as I said, I want at the end of this talk, you have some information, some ideas of what's going on and what are the challenges. The challenges are basically in this slide. Now let's try to understand a little bit more how they look like, okay? So let's look first at roles. Here you see some, I will put, I will give the slides, and the slides are filled with references. Please look at them, because I try to somehow to associate topics to reference as much as possible. So the first role, and this is taken, by the way, from a paper from Schultz, that has been very influential in 2003, which is about how do we formalize, how we evaluate human-robot interactions. And basically, there are other proposals. So this is not the only one. As you can imagine, when you say human-robot interaction, 10 people will have different ways of classifying what could be the roles. But this has been very influential and used very much. So also, somehow, I've been trying to focus on taxonomies, ideas, proposals that have been a large impact in the community. So the first role is probably the most obvious, is supervisor. So what is a supervisor? So supervisor is, in kind of general sense, someone that manages goals. I tell the swarm what to do, monitors what is going on, and control the overall situation. When I say here manages goals, it's very broad, right? So I tell you what to do, I tell the system what to do. I want basically to drive the system to achieve what is needed by the mission. But just imagine your supervisor, who is a PhD student? Okay, a lot. What your supervisor is doing is precisely doing this. Trying to make you achieving the goals of your thesis, keeping a continual interaction, monitoring, supervising you. So the idea is we can do the same with a swarm. Or we can act as a peer. So a peer would be like your colleague, PhD student, under the same supervisor. And what do you do with a peer? Well, with a peer, you interact, you exchange information, of course. So it can change your local way of doing your research, but somehow the general goals are still defined by the supervisor. And then can also be a bystander. So a bystander is basically there, is interacting, but actually has no way to change your general goals or intentions. But of course, the presence of bystander can affect what the swarm is doing. Okay? So it makes sense, right? Very simple, but 3 categories that actually summarize what a human can do. And so this is, as I pointed out, is a classification very much used in human-robot interaction. So if we expand a bit more what the supervisor does, actually, and this is taken from Sheridan, this handbook of human factors and ergonomics. Again, this is a very influential paper. This is professor at MIT. What the supervisor does? Well, a number of activities. So planning, what tasks to do. Of course, again, think about your supervisor for your PhD, instructing. So basically trying to tell you how to do the things through provided an interface, okay? Your supervisor say, okay, you should do research on human-swarm interaction, then I should tell you somehow, provide a high-level way how to achieve what you have to do. And then monitoring what's going on in order to detect any problem, to assess progress. And of course, must be intervening, take control if things don't go the way are supposed to go, or when something has been achieved, so let's set a new state, a new goal. Last but not least, that your colleague was somehow pointing out, learning. So I observe what's going on. If things don't go the way I expect, I should rethink the way I'm doing my supervision. So if my student is totally wrong every time, it's not necessarily his or her responsibility, but also mine. So I should learn how to interact, how to do my supervision, okay? So it makes sense, right? So this comes, actually, this classification, the taxonomy, from a more general field, which is human-machine interaction. Okay, I a little bit adapted the wording, but it makes sense, okay? And actually, if we take everything together, what we want to achieve as a role for the human and the swarm together is to obtain what is termed a mixed initiative system. So what is a mixed initiative system? It's something where the roles are not, let's say, statically defined. I'm the supervisor, you follow, shut up. No. Let's do things together. And then it's like you as a student proactively say, hey, professor, I don't understand this. Can you explain more? Instead of me trying to understand if you have understood what I'm saying. So there is like a proactive action from both sides, so both sides can intervene. And this is called a mixed initiative, because there might be initiative from both sides, and then both sides have some certain level of autonomy, awareness, and they can help each other to realize the big mission goals. So let me just point out a few examples of a human that could act as a supervisor. And I'm taking examples from the literature, okay? So trying to ground what we are saying to what has been done so far. So one thing which is pretty obvious, I would say, this is coming from the Guardian project. The Guardian project was I think it's British project in mid of year 2000. And the idea was to develop robotic technologies to support firefighters, okay? So one thing is, hey, I deploy firefighters and robotic swarms, robots in the field, and then I'm sitting in my room somehow, and I have my interface. I assume there is information which is flowing to my display, and then what I do, I set mission goals, I keep monitoring, I keep reassigning, scheduling, intervention, and so on, okay? So basically manage the swarm remotely from a control center. Another thing is, in terms of supervision, is I can do teleoperation. You might say, hey, you want teleoperate a swarm? Yeah, why not? If we have means to do it. So for instance, in this paper, what they do is to actually, so we have this, these are small robots. This is an object that should be grasped or transported. And the idea is to attach to his finger a control point. And the control points are with they call the synergy matrix, are projected into the robot swarms such that any movement with my hands is transferred to the robots through this synergy matrix, basically to a dynamical system. So you can imagine that now, okay, the robots are only 5, like the hands, fingers, here are 6, but then in a sense we can do simple things like this, or we can grasp, move, and other things. So this would amount to have a supervisory control in the form of a teleoperation, okay? Of course, I need a means to observe what's going on and means to send out my information that has been processed, this synergy matrix, to the robot. Another example is what is shown here. Basically, I have this mobile robots. I can steer the robot. I can, on my display, I can say, okay, this is the direction to move. And then this information is passed as a virtual force to the robot, or like a virtual attraction point as a waypoint. And then the robots will, according to their position, according to some noise, somehow will move in the desired direction. Very simple. Or we can do something like, we can use gestures for discrete group control. So for instance, I want to control a few robots or even a group of robots that are in front of me. And so I can do what Jawad here was doing. Which is basically letting the system recognizing the gesture. The two globes are used to define a sort of a cone, and the system autonomously, by vision, by recognize the things, and basically can select multiple robots. Of course, this is supervisory control because I'm locally telling the swarm what to do. Okay, we will see later on a bit how these basic capabilities can be combined, like in this case. So you can have multiple gestures, and then you can make a phrase and tell, hey, you two, take off, move in that direction, and move in that direction for 2 meters, just using gestures. Of course, this is supervision because I'm setting the local goals, giving the instructions to do what the robots need to do. An example of, instead of a robot as a peer, still in the Guardians project, is when you can think robots and firefighters are in the field and they work cooperatively for the same task. So the task is, for instance, to find survivors, to detect fire and other things. So we can do things together as long as the robots are autonomy enough to perform this task. Another thing which is quite interesting, and pertains to this part of the story, the robots, so the firefighter has some sensors, so the robots can detect the firefighter locally. So basically, they autonomously, they split in groups and they follow the firefighter, like is illustrated here. And they use their sensors to detect obstacles, smoke, fire, so hazard for the firefighter that otherwise this guy cannot really check these things. And so basically they detect things in advance and they steer the motion of the firefighter, projecting. So they have some consensus. Again, there is local autonomy. And then they steer the firefighter in the direction showing this on the mounted head display. So in this case, basically the firefighter will see this information and then this tell that he should go in this direction and not in this direction because probably this direction is not appropriate and can have some threats. So in this case, robots and humans, they are peers. Okay, the human is not executing any supervisory control, but actually is profiting from the presence of the robots. Just also to give an example as a bystander, this is like funny things. So one thing could be actually this is times 5, so the music is the most appropriate for this scary situation. But you can leave it because okay, it creates the atmosphere. In this case, the little girl, imagine can be a person to be rescued. It's total. Okay. Maybe I'll switch it off. So basically, in this case, the girl is a bystander, does not really do any supervision or provide any input. It is like something that the robots helps to move on. By the way, the girl was really super scared for the entire experiments. At the beginning, there was the mother holding the hand because she was really scared, which is also comes back with who said the robots should not actually guarantee safety. It is not obvious how the acceptance. I see all these little things coming to me, and are they smart enough not to bump on me or hurt me? So this definitely this matter. Another example of humans and robots as bystanders is actually in navigation. So humans and robots can share navigational spaces, so can be anywhere. Then again, we need to have ways to design the robot behavior, sure, but also the awareness from the human side in order that things happen the way we want, okay? And I don't know, probably you're not gonna be able to see this. So this is no, you don't see it. All right, forget it. So this was actually, we developed, had some publications on IROS and ICRA on bio-inspired navigation system, inspired from the way humans basically navigate through crowds, and we put in on robots, and the idea is if we take something from humans, and we know how to socially interact with each other, to move one with respect to the other, then we take this to the robots, then probably we have a behavior of robots, even in a swarm, so in a crowded situation, which is quite acceptable for the humans, okay? By the way, you can even try yourself how good you are as a supervisor for a swarm, trying out what is crowdsourcing swarm control. It was put like 2-3 years ago. I don't know how many people have been playing, but basically you can go here and playing these things. Basically with the arrows, you control the swarm, giving like steering directions, and you have to achieve certain tasks. Like in this case, you have to move this block into this kind of other place, okay? Believe me, it's not easy and obvious. Please try to do it because it's quite funny. I tried at the beginning, it's a disaster because you have all these robots, you give like a bias, and then things totally don't go the way you are expecting. But it's a way also to understand, in a sense, how difficult is even the simple idea of having a sort of teleoperation at swarm level. All right, so if we go back to our diagram, so somehow we have explored roles in terms of supervisor, peer, and bystander. I hope now we have like a clear understanding of what these roles can be. Now let's move on in the sense of once let's say I decided what should be my role. In the following, we will focus on the supervisor because at the end it is the most interesting one from the point of view of designing what the human has to do. Then I have to focus on the implementation of the role. So I want to be a supervisor, fine, with strong control, for instance. So what kind of interface I should use and what kind of controls I should send to the swarm. Well, in order to answer these questions, I need also to clarify what is the level of autonomy of my swarm. Because as I said, if the swarm is not capable, then maybe I should try to help it as much as possible. If the swarm is very capable, I can give like little hints, and then it's gonna do the job. So the things are very much interlinked. So in order to talk about this, it's useful to point out the notion of levels of automation, which again is a notion that has been very much used in the context of human-robot interaction and in general human-machine interaction. So the levels of automation, in a sense, defines what kind of relationship between the humans and operators and the technology are being established based on the respective capabilities. Again, in the work from Sheridan, he identifies 10 different levels of automation. So somehow we go to the fact when the computer offers no assistance, it's just a piece of mechanic, and the human has to do everything, has to drive, at the end of the day, the entire system, to the level where the computer decides everything and acts autonomously, ignoring, not needing at all the human. Somehow I think to grasp this is, since nowadays there's a lot of talk about the self-driving cars, these kind of levels of automations they found their relation in the field of automotive, and for instance, the Society of Automotive Engineers in the US have defined this 5 levels of autonomy, where we start from no automation, then there is assistance to the driver, there is partial automation, conditional automation, high automation, then full automation. And you can see it's just like grading the levels to which extent the system is capable to do things by itself. All right, but maybe this is a bit too much for our purposes. In principle, if you want to have like a human-swarm interaction system, the swarm must be able to do something, right? So let's say it should stand at least from level 7 that does some automatic execution of goals, intentions provided by the human, and then informs the human. So if we want to actually take this and make it a bit more tailored for human-swarm interaction, what we can do is to take another taxonomy where basically we start with a system where the level of autonomy is full autonomy, in the sense that the swarm is capable to do everything by itself, to what is termed machine-oriented semi-autonomy. So the idea is that the swarm informs operators of its special need, but it does it sporadically. So it's not like keeping saying, hey, I need help, I don't understand. No. Things happen, I need to be informed because I'm in the loop, but this happens, let's say, at low frequency. So it doesn't overload the operator. And makes most of the decision without my direct intervention. On the other side, we can have the human-oriented semi-autonomy, where at this stage, the swarm needs to inform the human operator very frequently, meaning it's not really capable of taking most of the decision by itself. And the manual operation, where basically the operators make all decisions and actions for the swarm. So these 4 levels of autonomy are, I would say, more appropriate for a human-swarm interaction. These have been actually adapted from this survey. And we can term, probably Professor Franchi has introduced this notion of shared control. So we can actually term these 2 aspects are shared control. So basically, I do something, you do something, and then we interact in helping each other. And again, this can be framed in a more general terms of a mixed initiative system when the way interaction happens is very proactive. So basically there is an autonomy for the machine deciding when and what to ask, okay? Which is not obvious. Imagine you have a swarm, you have to get out of this room and all the doors are closed. So the swarm is actually capable of climbing, going up to there, and then can move away. So if the swarm is capable of understanding that doors are closed and they could be opened, then proactively can ask the human operator to open the doors. And this would be a fully mixed initiative system, but requires a certain level of autonomy as well as the capability to assess situational awareness very precisely. Okay, so let's say we have sorted out the aspects of roles, levels of autonomy. Remember, there was this keyword, cognitive effort. So let's assume I know what the swarm can do. I know what I would like to the human operator doing. Is it feasible? Somehow, in terms of workload, in terms of cognitive effort. So the question is, how complex is supervising a robot swarm? How do we quantify this? Well, in computer science, we use the notion of computational complexity. Basically, we say, hey, listen, we can define the scalability, tractability of an algorithm as a function of its inputs for very large inputs. Okay, so the big O notation. Can we use something similar to quantify the complexity of controlling a swarm? Yes, people have been doing something similar. Because somehow we can see the task of controlling a robot very similar to what an algorithm is doing, which is repeating doing things until we reach like the desired goal. And with human swarm interaction, what I'm doing is, in principle, keeping interacting with my system until the system does what is compliant with the goals. So in human-robot interaction, the operator's cognitive effort, also I mean the workload, somehow can be put in equivalence, an analogy to the computational complexity of algorithms in computer science. So we can indicate with a big O notation like this, a cognitive effort that scales linearly with the size of the swarm. Then we say, sounds good, it's linear. Well, well, yes and not. Because while this is very nice in computer science, because we have a computer doing the job for us, when something is linear with the number, it might mean like 100, 1,000, 1 million, so the swarm grows a lot, then I'll be necessarily overloaded. In general, let's say I can have one operator for multiple robots, and the cognitive effort, we will see, depends very much on the dependencies among the actions of the robots. If I have one operator for robot, and robots are independent, then actually the control cognitive effort is of 1. Because I can, basically I'm assigned to one single robot, that's all. End of the game. But of course, this is not the situation that we can usually have. So let's see a little bit more in detail. So let's consider the case where we have n homogeneous robots performing n independent activities. So this could be the case, for instance, I have like a search and rescue mission, and so this is the area to survey. These guys are UAVs, robots. So what I can do is assign each robot to a different portion of my environment, and each robot does its job there. So basically, they are independent, and they do not really interact with each other. So how would the supervision would work? Well, as an operator, I would actually switch my attention to one robot to the other at a time, right? Makes sense. So I need, of course, to have some schedule for doing this, but let's assume the robots are all the same. The areas have been assigned are more or less equivalent, so I can, 5 minutes, I keep watching one, 5 minutes, next one, and so on in round robin. Fine, I'm done. So, of course, more robots imply more effort, but the overall cognitive efforts increase linearly with the number of robots, so I can say that actually it goes like O(n). If the number of operators is also increased linearly with the number of robots, then, okay, I got the magic, because then the cognitive effort for one single operator goes to O1, because every single operator just takes care of one single robot. But again, sounds good, but would hardly scale for real swarms, where if you have 1,000 robots, I cannot have 1,000 people, each one taking care of a robot. By the way, I've been working a lot in search and rescue things, and there was always this dispute with people saying that according to the laws, authorities, and things, you need at least 1 or 2 or even 3 operators for each UAVs, for instance, or for each robot. That basically would totally stop any research on using multi-robot systems in search and rescue, because you need an army of people just to take care of the robots. You need all the line of sights and other things, okay? So, there is another aspect. When I do my simple thing anyway to switch my attention from one robot to another, what I do, basically I start with Martin, then I start with him, you, and so on. Well, but then he's left unattended. And what this guy is doing, I don't know. So once he's unattended, he can make problems, right? So this is called, actually, is neglect time. And things can go wrong there. We would need, in order to have a good schedule working, even in the linear case, to have an estimate of which is the maximum time a robot can be left unattended without its performance being degraded, compromised, and all. But this is very difficult things to estimate, and this, by the way, totally depends on the task. Okay? So this is to say that actually we have the big problem how to schedule operator attention in order to minimize the consequences of neglect time. There's been a lot of work in this respect because it is expected that somehow, even if I look at subgroups, now I focus on this subgroup, and then this subgroup is left unattended. So how long I can focus on different subgroups before things get compromised? This is like quite interesting and complicated problem. We can draw like a simple model. Individual robot control by single operator doesn't really scale. Has a number of problems, doesn't scale, and also the more autonomous the robots are, the better is in terms of reducing the impact of neglect time, but still the problem is there. These are like a number of references about this problem, and especially about the problem of neglect time. So what we can do is, hey, why don't we control multiple robots at once, right? Instead of single one has all these problems. Well, if we take the same problem as before, now what we can do is we can draw, for instance, this area, and then say, okay, all these robots get assigned here. In this case, my controls, the cognitive effort is independent of the number of robots. Only my cognitive effort is actually in drawing this. Then I assign all the entire robots there. So my cognitive effort goes magically back to 1. This is indeed quite attractive. And it suggests that if I look at this swarm as a group, as a system instead of individual things, then things can start to scale and can start to be affordable. However, if I have dependencies, things get complicated. So for instance, think about this box pushing with occlusions. And I would like to have like an operator helping them. So they have to move the box towards this red, but of course they don't see it, they are too short. There are ways to make them eventually achieving this result, but if I want to have an operator inside there, then how do I intervene? It's kind of complicated, because now the actions of all these guys are actually, even if I split them in groups, they are interdependent. So I will need to focus my attention on groups of robots at the same time. So when we have dependencies, my cognitive complexity becomes superlinear, precisely because of all these dependencies. So, actually, let me put this model first. So, what we can have is, in human-swarm interaction, thinking about cognitive complexity is a useful thing, because we quantify how hard it is for a human to do his job, given that I decided what the role the human should have. The control on the individual robots doesn't really scale. Group control is definitely the way to go. And robot dependencies that would need to be managed by the operator should be avoided. So the system might have dependencies, will have necessarily, but I should as much as let the system, the swarm, with its autonomy to deal with dependencies rather than take this on me and trying to manage directly dependencies, because then my cognitive effort would explode. And this is, okay, an illustration of how, with respect to the number of robots, the operator resource, so the cognitive effort is growing. So in this case, we have OD1 is very nice, then it's linear, and then this is an illustration that when it becomes super linear, then will explode, and things are not affordable anymore. By the way, in this simplified view of effort, I'm not taking into account a number of things, which are, for instance, the load, cognitive load relative to interaction, to do the things. And also to gather the information from the swarm and to build a situational awareness, which is very, very demanding from a cognitive point of view. So I'm just somehow simplifying things in terms of controls. So this is to say that somehow this O1 is an ideal abstraction. Things are, in general, more complicated. But it's a useful way to think about this before you start like designing a system. All right, so if we go back to our diagram, somehow we have dealt with this part. Let's see, and also with the autonomy levels. So let's focus more on the interaction interface. The interaction interface includes how we send out the controls and how we physically interact with the swarm, okay? And also how do we build situational awareness. Now, somehow, this means where the Yuma swarm interaction happens. So now I'm talking about the interface. When I say where, am I here sitting down here and the swarm is down there, or I'm here and you are the swarm? So basically, is the interaction remote or proximal? This makes totally the difference. How operator controls are physically issued. Are issued using instrumented modalities. I use this. You guys followed me. This is instrumented. Or I take out my hands and just use my voice and other things. It's totally uninstrumented. There are pros and cons for both things, right? And how the information data from the swarm is gathered and represented in order to build situational awareness. This is basically deals with physical implementation choices of my interface. On the other side, once I have decided how things happen physically, I should decide how to operate my control strategically. If we go back to the cognitive aspect, should I operate individual, group? Should I send information in the environment? Should I give information to some leaders? So how these things, how information is being transferred. So basically, the types of supervisor control modalities. And we can identify 4 different types that we'll analyze. Switching behaviors, which is basically you have a library of behaviors, and I decide, now you run, now you stop, now you jump. Fine, it's all on me, the schedule of what you do. Or changing parameters, you have internal parameters. For instance, minimal distance between you, yourself. And then I tune this distance, minimal distance, and you would possibly change your behaviors. Or I can control via environmental influence. What does it mean? If I write here a big post-it, the lecture is over, you all go out from the room. So your behavior will be a reaction of my altering the environment. Or I can control via proxy agents. So I tell, hey, you are my proxy, I give instructions to you, and then you try to influence all the others. Okay? So we have different ways to do the controls. And different ways, of course, have different workload, different impact, different complexity. So this pertains with strategic choices. So let's look a little bit at the different things, how they can happen. So first, when I say remote human-swarm interaction, when I say instrumented, so I mean something that some guy is somewhere, for instance, in the control center, and the swarm is deployed somewhere else. Somewhere else, what does it mean? For instance, in underwater, or in space, or in large areas aerial, or distributed for logistics, or in some fields that are dangerous or inaccessible for the humans. So it makes sense to use a remote interaction in all these cases. And these cases are very much interest. Okay? Of course, we need bidirectional communications need to be in place, because I need to have here some feedback in order to build up my situational awareness. This is an issue. This is a problem. In some cases, we can achieve nice communications. In other cases, might be difficult. For instance, if I am underwater, by the way, yeah, I can have some transponders on the surface, but communications are so slow. So if I operate in control, I have to take into account the delay in things happening. Or if I want to send, actually these are, it's funny, I saw these other footbots, robots that were built in Swarm project that are like this. They were put by somebody on the moon. I don't think they will ever go to the moon. But if I have to control a robot which is on Mars, then I have to account for the delay between my controls and what will happen and the feedback, which frame the problem in quite complicated way. And so when we have communications between, and also communications can have can be intermittent, can have errors, can have limited bandwidth. So all these things will constrain the way things will happen. Instead, proximal human-swarm interaction is when basically this swarm and the robot and the human share the same environment. Okay, so like in this case. So not necessarily the entire swarm is in the same place, but somehow parts of the swarms are accessible directly to the operator. Okay, this is quite natural model for somehow mixed cooperative teams that are deployed in the same field. So if I want to do search and rescue, I will deploy my rescue agents and my robots together, and they will be in the same environment. So it's a totally, I would say, different configuration and different applications for the remote applications. It can be implemented using either instrumented or uninstrumented methods. The remote requires instrumented methods. I need devices, I need communications, I need displays. Okay? If I'm here, as I said, I can get rid of this, and we can start interacting just with voice, gaze, and hands. So when I say instrumented interfaces, can be anything of these things, by the way. Tablets, augmented reality, joypads, haptic interfaces, dead cameras, wearables, anything that allows me to interact, to gather information, to fill information, to send out information, to represent information. An instrumented interface, well, typical things, for instance, can be like, this is an example of facial engagement. I can use gaze and gestures, or I can just use only gestures, or I can use gaze and speech. So everything that basically I can use with my body, this could be like appropriate. And in some cases is the way to go. Again, imagine you have, when I was like having this, a lot of projects with in search and rescue in Switzerland with civil protection, the rescuers, the guys said, listen, we are there working, we need hands, we need to see things. I don't want you to give me wearables, displays, tablets. The only thing I want to use is my hand and my voice, over. And I want to use the way I like it. And sporadically, by the way. It's not like, hey, please, no, move a little bit. No, okay? So actually, the use of uninstrumented methods is essential in certain contexts, in say proximal scenarios. Okay, so let's see what kind of behaviors, what kind of controls we can operate. So somehow, we said, can be like remote or proximal. We can use instrumented or uninstrumented. Now, it comes the moment, how do I control my swarm? All right. So the first modality is switching behaviors. So the idea here is actually, I took this from Apple somewhere. You can have like a library of behaviors that you are able autonomously to implement. And then as an operator, what I do is I select your behavior. Done. And then you execute it. So this actually requires high level of autonomy from the side of the swarm, necessarily. And the communications, of course, need to be reliable. From the experiments people have been doing, looks like good options for novice operators for interacting with Swarm, because it's very simple indeed. You just have to select from discrete set of possibilities. What is important is actually the operator needs to have a solid situational awareness, because if I have to decide, now you start jumping, and then you start running, when this switch happens, I need to understand your state, I need to understand this with respect to the mission requirements, and then I need to schedule it properly in order to achieve the overall mission goals. So actually, the workload seems to be simple because I only have to select a behavior, but actually can be quite high in this respect. Another modality for issuing controls is by changing parameters. So what is the idea? Remember, my swarm system is actually a complex system, right? I said at the beginning. A complex system is a system that usually, based on the internal parameters, can display multiple or complex attractors, okay? So why not simply tune your internal parameters in order you to switching attractors and then reaching different stable states? This is better, it's less sharp than you jump, now run. No. Let me switch things, and things will happen by self-organization, magically, if the system has enough structure to exploit these emerging aspects. And what is interesting is that parameters do not directly influence the behavior, but rather is more subtle, because basically have indirect effects, behaviors that emerge from interaction within the swarm and its environment. So it's not the swarm only, but since I change your parameters, you keeping acting, and then you have also the feedback from the environment. So for instance, this is an example from this paper, quite a nice paper, indeed. So they were like analyzing, for instance, in nature, you have systems like animals, for instance, having like a sort of like circling behaviors around a prey, or you have some flocking behaviors to escape, to run away from predators. How do you switch from the two things? Of course, you can say, hey, I see a predator, you switch. But another thing is actually to tune the internal parameters. And they show, for instance, you can have this torus behavior where actually the animals, the elements keep like circling around a central point to move to a flocking behavior, just changing a parameter which is a radius of orientation, let's say a parameter which is related to the internal forces among the agents. So I just change this parameter, which is related how basically all the robots define a sort of center of gravity, and then magically I can get like a transition between one attractor, which is flocking, to other attractor, which is torus, which is quite nice indeed. But of course, requires to have a good understanding, a good model of what's going on, and the use of virtual forces model is very effective in this context, and I would say it works well precisely when you have motion-related behaviors. If you have more complex behaviors, the situation becomes way more difficult to achieve. Another control modality is by the use of proxy agents. So we saw, I just click and change behavior. I change your internal parameters, and then what I can do is say, all right, isn't it easier just to define my proxy, so to define some agents that are informed, become informed in an uninformed system, And then they locally influence the other with their informed behaviors. It's pretty easy. In nature, this happens quite commonly. One of the things that was most surprised about this was about locusts. They understood when you see all this swarm of locusts that seems actually to move all together. No. Actually, there are like a very tiny percent of them, like 2 or 3%, that are, if you see all the trajectories, they move incredibly faster. And these are the informed individuals. All the others, so these are the leaders, all the others are the followers. And the entire locust swarm behavior is just dictated by 1% of informed individuals that are able to drag all the others. So indeed, leaders, followers, is a behavior that works very well. Nowadays, we have the influencers on the internet. These are leaders somehow, and there are millions of people following them. So it works. It's easy to set up. Here is an illustration. Basically, you have a system. This is a system actually for from the guy at the beginning for the list of properties, desirable properties for a swarm. Basically, you can set an avatar or like a proxy or whatever you want to call it inside the swarm, and this guy will interact locally. So we preserve locality with other members and will affect them. In turn, these guys will be changed and information will propagate. You can inject as many leaders as you want in order to create a stable system that evolves and according to the desires of the human operators. This is another example where actually we want to change, is from the same guys, the slide before. We want to change the shape. Before it was just changing from torus to flocking. Here is, hey, I want to have my system taking any shape, for instance, for perimeter shaping, circling things. Then what I do is actually to set some mediators, some spatial agents at certain control points, and again, based on virtual forces, they will create the entire perimeter and organization of the system. So again, you can play with many different ways to obtain the desired results using proxy agents. A last way to exert controls is by environmental influence. The idea here is basically what I represented here. So basically, it's like Post-it. I write something on the board, you read it. In order to read it, you have to pass by here. So somebody who is in the other room is not going to read it. So it's a locality of information which is placed. And this locality affects only the agents that locally can interact, can gather this information. And you can do it in two ways, by the way. You can physically change the, so this is actually what happens in our roads, right? Basically, we get information if we take this way, where to go, and how long, how many kilometers are there. So it's all influencing the environment, and you need to pass by. Of course, you might say, hey, but if I have robots, how can I keep changing the environment? What should I do? That's not obvious, right? Yeah, you can leave beacons. Fine. But, hey, then who is going to remove those beacons? So there is a problem with this model because in principle it requires that you physically modify the environment, which is not something that you can usually do. So another way to obtain the same result is actually to have the information being carried on board of the robots. So for instance, look here. Okay, it doesn't see very well. So this comes from this project, and they're looking for an intruder. Each robot has virtual pheromones on top, meaning has information about where the intruder is located. So I'm here, according to what I've been receiving information from the others, observing, I know that the intruder is in that direction. So my arrow will point in this direction. If I move here, my arrow should actually keep pointing in that direction. So what does it mean? I carry with myself on board information. So the information about what I know is only accessible here or around me, okay? And it's information which is consistent with my spatial position. So I do not modify the environment, but rather I bring information with me and I keep making this information consistent with my motion. This is quite effective because, again, what I can do as a user, I can either modify the environment physically, and this is actually, I can do it as a human operator, or I can take an avatar, again, a proxy, and to this proxy, I give information which is being related to a specific spatial situation and is being carried around and being updated accordingly. This is actually, I would say, the most, it's a signature way of interaction and learning in swarm system. Because this is the way ants, bees actually communicate, because it's all these pheromones. With the pheromone are chemical traces that are being left in the environment, so are physical modifications in the environment that are only accessible to agents that pass by. But for instance, bees, they don't only really leave information in physical environment, but they have like, they release pheromones by physical contact or around them. So you need to get in touch. And this pheromone information, which is, for instance, information how rich is a crop of flowers, is being carried with the bee while the bee moves, and the information that the crop is there is being kept up to date constantly. So this is somehow the most swarmish way of controlling something and transferring information. Okay, I think I should finish. I had, so basically what we did was try to look a bit what are the issues in human-swarm interaction in the terms of design, okay? I'm really thinking you sit down, you want to design a system, you need to know what are the elements you have to deal with. So basically the elements you have to deal with are how you design human agents, what kind of roles, their cognitive complexity, how you design, how you decide the interaction interface, where the agents and the swarm are located, what kind of tools you use for the interaction, how you transfer the controls, which are all these 4 methods, how you affect the behavior. And each method has different pros and cons. There is no, I would say, ultimate, final recipe that works for all of them. And of course, we have to take into account what are the autonomy levels of the swarm in order to take all these decisions. We didn't really see this part about situational awareness. I warmly suggest you to look at this paper from my colleague Katia Siqueira and her collaborators, which is a nice survey, the only survey quite recent about human-swarm interaction. You will see a lot, 200 references and things, quite rich, and pointers also with a number of references I already discussed it. Okay, I added here, but I'm not going to do it. I'm not going to take my time. I had actually a number of examples with videos. Actually, that was the fun part, but okay. I will leave these things in the slides, okay? And also I will add the links for the videos so you can actually see it, because most of them are quite entertaining and show. Show different ways of, like, for instance, this is like a swarm, a stigmergy way, so to control things. This is actually when we have a leader control for pushing a box. You will see it's very ineffective, but it shows the idea. Here you have actually the Antonio system for the flying ants, that actually you can control a system of UAVs with your hands for manipulation. And here you have a system where the system from the guys at Disney and ETHZ for having like an interactive system for controlling a swarm to create shapes somehow. And here you will have actually a lot of my work I did to create an entire gesture language for search and rescue, for interacting with a swarm that integrates gestures and speech to create sentences somehow, and also how to use a swarm itself as a distributed sensing system to recognize gesture, because, by the way, I didn't say it, but once we use uninstrumented methods, if you are the swarm, and say, if I want to use my gesture and say, okay, now everybody goes there. Well, you should see this, and then you should understand and get a consensus about what is this direction. You should understand that they said go there, the action, but also the direction. And the direction is not an obvious thing to estimate properly. Yeah, other things. And then actually, what was the last work I did when I was in Switzerland? In actually to use wearables. This is like a trend that makes sense nowadays, to have a human-robot swarm interaction outdoors. Instead of making the robots recognizing my gestures, I actually put wearables for myself. And then what I do is to integrate speech with gestures. And what I do is to send directly decoded information to the swarm, instead of the robots telling me what to do. I mean, they try to understand in which direction they should go. I try to detect my things. We try to establish a common reference frame, and then I say, okay, this is the range and bearing you should go. So basically try to make the robots as passive as possible, and this is also promised to avoid all the aspects related to illumination and so on. So you can have fun looking at these things. And then, yeah, as a summary, basically, I was just to say, we went through a number of issues. I show a few, I had it, and I discussed a few examples. The field is evolving. So I said, there is no final solution. If you are interested in this, please, I'll be very happy, actually, to supervise or collaborate. There are many user studies. So all the studies are based on real users, okay? So even when things happen in simulation, there is always a real user doing things, which is very good, indeed. Scalability and emergence are still somehow issues, but are targets to reach. I think the field is growing. It presents a number of difficulties, but humans are required to be there, as I said at the beginning, and I want to repeat it, in order to really deploy, according to my view, robot swarms to the real world. Okay, thanks for the attention.
Thank you very much, Gianni, for a great talk. It was really inspiring. Thank you. We have some time for questions, so please go ahead.
Thank you for your presentation. I have just a small curiosity, and I don't know if it makes sense, but anyway, as far as I understand, this is just one directional, from human supervisor to the swarm. But I was wondering if there may be some cases in which the robots can supervise the humans. For instance, you mentioned the search and rescue scenario. There may be situations in which the robots may have more vision of the environment and could direct the humans through safety paths where there may be fires or other dangers. So is there any work towards this direction?
Yes, I mean, there is this, in a sense, the work in this direction is there, but it's more in the sense of using the swarm as an augmented sensor, right? So I can use like aerial view, I can send things somewhere that is inaccessible for me, and then I get this information, and I use this for situational awareness, and then I take my decisions. And I think this is super reasonable. I mean, this is the most straightforward and very effective way to do things. It does not involve much complication. Will be interesting, and I think there is no really work in this sense, but maybe now with new AI developments, where actually the robots are suggesting decision-making, complicated sequence of decision-making to the human, which is what we do now. I mean, the human is actually suggesting goals or sequence of decision-making, so he's using superior cognitive abilities. So what if actually the robots, once equipped with cognitive AI, will start actually in a mixed initiative system providing like more insightful suggestions. But this is, I think, quite unexplored.
So thank you for the active introduction. My question was, let's say we get your example of drones trying to go out of the room and we have all doors closed. And the human decided to tune parameters to say, okay, now you go out of the window. Now the second time the swarm faces the same problem. Could they have a feedback loop to know, okay, like last time human told us to do this move or tune the parameters this way, and you can get a feedback loop, increasing the autonomy of our swarm by our supervision?
Yes, definitely. If you remember, one of the aspects of supervision was learning from the side of the operator. What you suggest is somehow to learn from the side also of the swarm autonomy. I think that this is totally feasible, and it would be the way, somehow is a good way to go, because especially at the beginning, even as an operator, I don't know what are the good parameters to set or to suggest you. So we can learn together in this respect. Actually, I've been doing like some work on for gesture recognition, where the idea is actually using multiple robots, which are quite nice, because if I want to show a gesture, I can place the robot randomly, and then I sample multiple views in one shot. But the idea is we have been doing some interactive learning online. So I want to learn a vocabulary, but then the swarm can tell me, according to misclassification during the online training, suggesting what should be the next sample. Let's say I want to learn the finger counts. Then, okay, this is easy maybe. Maybe, I don't know, maybe this, all right. Maybe this is a bit more difficult. Why? Because if I see it like this, might be 1 or 2. If I see this is 1, this is, and then the swarm was able somehow, based on some entropy measure, so some internal feedback, to suggest what should be the next sample. And so what you're proposing somehow in the same direction, you get like an internal observation, and maybe it can be like a mixed initiative, it can be the swarm suggesting, hey, maybe we should change this parameter, or say, hey, I think I would do this. Is this fine? But again, we should go to what is a more complicated mixed initiative, which is, I think, is where we should aim to.
Okay. And also a second question about the locust example. So you said you have only 1 or 2% of the locust being the leaders, and all others are actually following it. So what if in any swarm I could introduce 1 or 2% of malicious agents and make the swarm behave the way I want it? How could this be mitigated?
Well, I mean, in this case, it's very hard to generalize. Maybe Gabor, if you see here, Yeah, maybe you could suggest more things, but somehow I would say in the case of it depends also on what kind of behavior, because for the locust is a sort of flocking, which is relatively simple because we have one direction and we should create a system that moves in that direction. If I have to do something which is more complicated, even I would say like doing clustering, that is a very good application, doing robot clustering in order, for instance, to clean up after a sport event or other things, then it's not obvious that certain behaviors that from super informed can easily 1-2% can make the entire system doing the job as should be done. So I wouldn't like generalize it somehow.
Do you have any thoughts on if there's a possibility of multi-users, and what's the possibility of some malicious person coming into the picture as well? And let's assume that not even malicious, let's assume also it could happen like between two users to give different instructions to the swarm, but in different clusters, and when they find each other, they say like, well, we were told to do this, and the other section say we were told to do the opposite thing. Do you have any thoughts on that?
Well, this is related to the situational awareness. So if you, okay, one thing is you tell me I do different things, or if I start observing that you do different things. So there is a deviation between what I expect and what you do. The problem is also in terms of transient states. If you start doing things that do not seem to me aligned with what I expect, but eventually they will get to a final state achieving my goal, then this ability of detecting this depends on how much I understand, again, how much do I understand what's going on inside the swarm. And this is a big problem. I didn't touch it, basically. This is a big problem. Because if things happen in time and the behavior might be weird, then what is my ability to understand what's going on, to foresee your behavior? It's very difficult because, again, it's a complex system, and then all the transient states predict from a transient state what will be a final state is inherently extremely complicated.
Another question?
Thank you for this talk. I'm wondering if there is an application or would be an application that human, not only the supervisory action in swarm, but is it not, but kind of a part of the swarm. And do you know any application of this, or could be an application in the future?
Yeah, in a sense, like the things I've been mentioning about search and rescue, for instance, or anything cooperative cleaning, this can be done, can be seen as a peer. So like supervisor as a peer, because somebody, the control center, some authority, say, okay, guys, you should find for survivors or fires, gas leakings. Fine. We have the same job. You're a robot, okay, I'm a robot, you're human, okay? We go around, as long as my autonomy allows me to do the job, I'm fine. And actually, in a sense, we want to go in that direction, but still we can profit from local interactions. So the idea is, I still have my high-level goals and intentions that have been given by some central authority. But then, locally, if you spot something, you can tell me, hey, I go watching there, you go watching there, just to be sure that we split the things together, or you can profit by my abilities to see things. So we can locally interact, and this is why actually instrumented things, gesture, speech, can be very useful locally because I can give like very simple commands or special indications or other things, and we have like peers in a mixed system.
Yes, thank you. I have also one question. It's not a question only for you, but also for Gabor mainly, and for Heiko as well, maybe. We didn't address this yet, but we should, because we have a lot of young scientists here. Some of them want to work with swarms, like majority of them even, as we have checked. But maybe, of course, they know a lot of good robotic conferences like ICRA, IROS, RSS. But could you recommend them also the best forum or the best conference or symposium in swarms? Because swarms, it's not so clearly defined field, right? It's multidisciplinary. I have found a lot of different conferences. In some of them, according to my opinion, they are not so good. Some of them are better. So let me ask all of these three about your preferred conference, and I will be really happy to see if you have consensus there. So you are the first.
Okay, well, in a sense, the idea of swarming is swarming around. So you can find swarms in many different communities, taking out the different perspectives. Of course, apart the usual suspects, I would recommend like AMAS, which is top conference in multi-agent systems, because at the end, the swarm is a multi-agent system. And in AMAS, they like to work on the theoretical aspects and the coordination aspect very much, so it can be very fruitful. Then there is also the ACC, the American Control Conference, which is okay. It's kind of more, okay, maybe higher level, tough, but you find very nice work over there, integrating control and swarms. But okay, you need to be like very solid in control to access. And at the end, okay, there is also the ANS conference, which is, I would say, is there since years. There is always good things and bad things going on there, but it's definitely worth also as a complement of IROS and ACRA.
So I will ask for opinion the others. Gabor?
Sorry, I cannot really recommend like a regular conference. In my opinion, there are like two types of conferences. One is like IROS and ICRA, which are like really huge, and you find all kinds of things in 7 like parallel threads, and they give you like good publication possibilities and a lot of networking, but it's like a little bit not that personal. And there's this other type which is like much smaller, maybe like 30 people invited to like kind of a workshop, and I prefer to go to these to be able to discuss a lot of things with others, but these are not that regular. So, and also like there is the swarming aspect you can approach from the robotic side of view, and there are other conferences targeting the same kind of phenomena from the biological point of view, and as I see more and more of these collective motion and collective behavior workshops are like including some robotic stuff as well, and it's usually an interdisciplinary part. So if the swarm aspect is very important, I would recommend to at least try it once to be together with biologists as well, because it can be like mind-opening. But no, like I cannot give you like a concrete example because they're like occasional ones.
So there is no like biologist swarm conference which would be regular and which would be considered to be good.
I'm not aware of that.
Okay, thank you. And I expect some provocative answer here.
Well, so good that you mentioned ants, Gianni. So that's a tiny conference, but then you really, like everybody really is into swarms, and it's a small conference, maybe not so high impact, but you can meet many people, like everybody at the conference actually is in the field, so that can be fun. Also for AMAS, certainly a great conference of high reputation, but they always expect quite some theoretical part in your paper. So if you have a very practical paper doing mostly robot experiments, they will not really appreciate the work, the hard work that went into your experiments. So if you have a good like theoretical model also, then AMAS is a good option. Then so if you have a lot of robotics in your paper, then I would go for IRO's ICRA, because they really appreciate hard work on actual robots. And then one that hasn't been mentioned yet is A-Life, maybe. So there's the conference on artificial life, which is a different community, right? So they're not focusing much on robotics, but still they appreciate it. And it's also a nice experience to see other stuff sometimes. And so I would also recommend that. It has been of high quality for a while. I'm not up to date how it is. So it is actually this week right now in Newcastle. So since you're here, you're not interested in A-Life, it seems. But maybe next year you can think about it. Yeah, it's a nice, very diverse conference where you also can place swarm robot stuff.
So one more thing that came to my mind is that one other problem is that many different communities call the same things in very different words. So for example, this swarming can be called like collective intelligence in one community, or collective behavior in another community, collective motion to some extent in the third one. You can talk about like agent-based modeling, or even like network science, and these all like cover like overlapping parts of this whole thing. So it's kind of hard to define. But if you collect all these buzzwords, you have more probability to find something that fits your interest.
Perfect. Thank you for your answers, and thank you, Heiko, that you prefer to come to Prague, not to A-Life. So thank you again very much. Or is there any other question, or do you want to react on this small discussion? Yes? Excuse me?
Just a book recommendation could be also useful. Another
so there is only one. Okay. So I will not ask Heiko for his preferred book. Another question? If not, thank you very much again.
Can I? Can I just say one thing? I profit. I'm looking for a postdoc, research assistant, whatever, in Qatar for 6 months, 1 year, whatever. Is a project about water surface robots, area robots for cooperative monitoring. If you have any interest, just talk to me, okay? Sorry.
No problem, of course, everybody's hiring. Thank you very much for coming to Prague and accepting the invitation. This is a small present from us. Thank you.
Thank you.
And now we have a coffee break. We are a bit delayed, but that doesn't matter so much. At the evening, we have some space. I would like to tell you some important things. So let me remind you. The certificates. So I have signed all the certificates finally. So they are in the registration desk. So who is interested to get quite nice certificate? I have to congratulate my guys for the nice design. I really like it. So you can find there your name and take the certificate. There are also forms if you would need for your university to approve that you have presented it. Here your work, please fulfill the form and leave it there, or tell me or ask me for signature if you need a signature even there. Something else? To se zeptám řečníku potom asi. Jako řečníku myslíš? Okay, there is one issue, ethical issue. We are recording all the presentations here, and I have to ask you if somebody is against publishing this, because sometimes it may happen that your face will be in these records. And we are also going to make a short video about the whole event, so most probably you will be there as well. So if somebody is against to have her face in this video records, please tell us, and we will try to remove you somehow. And the same for presenters. I don't know. Just tell me if you are, if you have something against publishing your speech, because this room has the ability to record everything, so we did it. Amanda asked us for doing it for her, and we decided to follow the whole week. Okay, so that's it for now. Please refresh outside with coffee, but really just grab the sweet coffee and come back, because we have to continue soon with Alejandro's presentation. So in 10 minutes, 15 minutes maximum, please be back.